Good afternoon, everyone. Sorry that the lunch is slightly delayed. We'll try to keep it as crisp as possible. Our session is titled Moving Beyond Predictions at Scale. And we also think that this succinctly captures what we want to cover and what we want to take the audience to the next 30, 40 minutes. So, when we think about machine learning predictions in the terms of ad tech context, we are thinking about improving predictions all the time. You're thinking about improving precision, you're thinking about improving the recall, the incremental lift, and so on. But when you are working at a scale such as what InMobi DSP operates at, prediction is just one part of the puzzle. What really matters is that whether we are able to convert these predictions into real-time decisions and operate that at scale. Now, before we move on, I'll quickly cover an experience that we're all familiar with. The we want to do we are trying to influence the ad experience of the user here, right? So this is something that we're all familiar with. You sit casually walking, scrolling through your favorite app, and you suddenly see an ad for a shoe that you've always wanted. Now the ad will feel relevant, the timing feels perfect, and you now are engaged. You click on the ad, you browse, and then you go on to make a purchase. But at the outset, all of this feels quite seamless. But at that moment, it's a careful orchestration that happens in the backend. So within a fraction of seconds, the systems needs to evaluate who the user is, how much should I bid, what is the right creative to show to actually get you engaged and get on to make that purchase. Now let us go slightly deeper into what systems basically enable to make this happen. So if you look at the ad tech context and the ad tech ecosystem itself, when a user opens an app or loads the page for the first time, you see there is an ad inventory that is available for the publisher. So an ad request gets generated, and via the publisher, it gets routed to the ad exchange. Think of ad exchange as nothing but a real-time marketplace in the ad tech ecosystem. On the other side of on the other side of the ad exchange sits multiple DSPs, just like InMobi, who are actually receiving these requests and also processing it in real time. But here's the challenge: all of the processing, all of that you saw, figuring out who the user is, how much should I pay, what is the inventory that I need to show to the user to get the engagement, has to be returned back to the ad exchange within a strict millisecond latency of 150. Now, to add to this complexity, all the DSPs compete with each other, and that's what you see as bids, right? If I have to win the real-time auction, I need to bid much higher than what other DSPs are doing. And another layer of complexity comes in the form of heterogeneity of the advertisers that the DSPs work with. These advertisers are nothing but the customers of DSP. Think of DSPs as an autonomous agent that are acting on behalf of these advertisers, their customers basically, for their own welfare, right? So all these advertisers have their own set of objectives. Some advertisers wants to drive app installs, some advertisers wants to go after purchase, some advertisers want to have a better brand recall, some of them are optimizing for long-term value of the customers. Now, to bring in scale into the picture, so InMobi DSP evaluates close to 1 billion plus ad requests every day. During our peak, we see and process close to 3 million queries per second, which is basically the ad request that you see. And all of this now has a constraint that the DSP has to respond back within 100 millisecond latency. The complexity of the system can be broken down into 3 individual layers. First is to figure out the ad request has come from a user. Who is the user? What is the intent? What does the user want? That comes from the layer called as targeting. So the previous speaker just spoke about recommendation and personalization, and this is more like a continuation of it. So the second problem comes in that because the DSPs are competing against each other in the ad exchange, I need to figure out what must be the minimum amount that I need to pay so that I'm able to win on the user and show the ad. But all of these will lie flat if I'm not able to engage the user by showing them the right creatives. So now, given the complexity of the advertiser constraints that we are working with, such as budget, frequency cap, the latency constraints that we are working with, and also the sparsity of the signals, we do not really know who the user is and so on. Prediction lies flat because you are not able to engage the user furthermore, right? So the first layer where this shows up is in targeting. In the ad tech ecosystem, in the ad tech industry, targeting is typically considered a binary classification problem. You are trying to predict whether the user is going to click, the user is going to convert, or will I have a long-term value available from the user, or will the user remain loyal to the brand. But the predictions are important, but they introduce an inherent limitation. All the prediction models are backward looking. They work and look at historical data, train themselves, and they also try to reinforce the pattern they've already learned. But this problem is also amplified if you're going for traditional machine learning techniques, for example, LGBM, tree models, and so on, where these models perform extremely good at the two ends of the probability spectrum. When you have a higher probability, you for sure know that these users are the right ones to go after and bid. When you get a low probability, you know for sure that these are the users that you want to avoid. But the problem lies in the uncertain middle layer, right? Which typically forms 65% of the users that the DSP sees on a regular scale. Now, the question naturally becomes, how do we move beyond what we already know? And this is where reinforcement learning becomes a natural extension. So everything starts with a state representation. A state is nothing but an environment snapshot at any given point in time. And we embed this state with multiple signals that we receive from the real-time auction. Where is the user coming from? What has been his past historical interactions? What is the context that the user is currently sitting with? What are the advertiser constraints that we're working with? Do we have enough budget to explore? How many times can I show the ad to a user? So on and so forth. So on top of this, we train a reinforcement learning agent that can learn an RL policy to figure out how does it want to explore. So instead of asking the question whether the next user will convert or not, it tries to figure out who are the kind of users that I have to go after so that I'm able to derive long-term value for my DSP and also for my advertisers. So once this is done, the action state becomes simpler. It is almost binary here. Whether do you want to go ahead and bid or do you not want to go ahead and bid, right? So all of this gets completed through the reward. Now, if you just a couple of minutes ago, I explained that different advertisers go after different objectives. Some want to drive installs, purchase, and so on, right? So these rewards is what actually the agent is trying to optimize for. But the problem comes in that in real time, especially the latency, all these rewards are delayed. Now, so what do we do is we go after short-term proxy rewards, such as whether the user engaged with the ad, whether the user clicked, whether the user saw the ad until completion, and so on and so forth. So now that we know how we can solve for targeting using exploitation and also exploration using reinforcement learning, the next problem comes in the form of how do you value the ad request? So DSPs, demand-side platforms, typically operate in a perpetual cold start environments. You are seeing new advertisers every day who are setting up new campaigns. They want to go after new users, new geographies open up, so on and so forth. This means that you are working with very limited or no historical data. So this is exactly where your conventional bidders, namely the click rate estimators, the conversion rate estimators, typically tend to fail. They don't see enough historical data to start with the right priors, which means they take time for convergence, or in worst cases, they start to overbid and underbid, which is not going to give you any business value or any incremental business value, so as to speak. So we at InMobi, we approach this problem slightly differently. Now, another problem with these conventional bidders is that they are locally optimal. Each ad request is evaluated at the face of it, but it does not understand the ever-changing market dynamics. So at InMobi, what we have done is we have rethought this problem of bidding as an optimization problem under budget constraints. So given any ad request, you can associate a value to it. You can attach value to it. For example, in the previous slide, we saw how targeting works. Let's assume there is an oracle that sits above the bidding layer that can understand what the value of the user is, and it can provide to bidding. And then for each of these ad requests, the bidder has to also understand what is the minimum bid that it has to pay. What is the cost for the DSPs? Now, if I know these two, now the problem becomes much simpler at the bidding layer. It is about allocation of the budget, given that this is the value to cost ratio that you get for each opportunity. Now, this is a simple mathematical formulation that we have, but the problem is this is an NP-hard problem, which means it will not be able to go to production. So we have sort of like made this a greedy knapsack approximation problem, where where each of the user gets a value, predicted value, and a cost associated to them, and now the allocation happens basis which is that user that can give me the most value to cost ratio. So what we have also seen empirically is that we have seen a 22% increase in the overall users, in the overall organic users that we can drive in terms of cold start users who can get conversions, who can make a click, who can make an install and so on when compared to the traditional bidders. So we have taken this mathematical formulation and literally converted that to a practical system that is actually computationally feasible, and it is near real-time optimal and is also scalable. Now, while we have solved for bidding and targeting, all of these two, even though they can come together, the final piece of the puzzle is what do you actually want to show to the user, which comes in the form of creative. You can bid, you can win the auction, you can target the right user, but if you're not showing them the right ad, you are not going to engage the user. So most of the DSPs, most of the current modern DSPs think of creatives as a single product optimization problem. Now imagine this situation, right? If you know for sure that the user has just signed up for a marathon, and in such cases, most DSPs would show you a single ad for a shoe. But given the higher order intent that he's actually not trying to buy a shoe, but he's trying to prepare himself for a marathon, does it not make sense for you to show a shoe, a socks, and a bottle together? And that is exactly what we do at InMobi. So now, how do we solve technically on how do we actually bring these products together? So this is where we take help from the game theory, the cooperative game theory, where we use Shapley allocation on how do we want to put these products together. There are cases where you put two products together, your overall conversion lift goes up, but there are certain cases where you put two products together, the attention span of the user goes down significantly. So we try to model this, instead of individual products, we try to model two variables called synergy and the cost of attention. And we use that to allocate what products go together. Now this yields two very significant outcomes for DSP and also for the advertisers. Like I said, perpetual cold start is the environment that the DSPs operate in. There are new advertisers, new campaigns, new geographies, new users that you're going after, which means the cost of exploration for a DSP for an advertiser is much higher. When you run ads like this, where multiple products come together, the cost of acquisition of customers significantly goes down for the advertiser that is in exploration. Now, the second benefit of this is that the overall revenue density per impression for the DSP goes up. Basically, we are making more margin per every impression showed instead of showing a single product. Now, the third outcome of this is that you are able to understand the broader intent of the user. Is, let's say you just show a shoe and the user does not make a click, does not make a purchase, and so on. This means that you are narrowing the intent of the user. You are basically now able to tag the user saying that he is not interested in shoes, but what you do not know is whether he is not interested in shoes, socks, or bottle together, right? So this basically tells you that you are able to drive a broader intent. You are able to understand the user's intent more broadly rather than a narrowed scope. Now, all of this should ring a bell, right? So targeting influences bidding, bidding influences the delivery, creatives influences the user action, user experience, and so on and so forth. But all of this needs to come together at scale, like I said before. So the first layer is the targeting layer, which provides the downstream models with much richer signals. We have the embedding system sitting there from neural networks and so on. The second layer is where your RL agent lives, where your bidder, that is the optimization engine, lives, where your creative optimization engine lives. Now, in the third layer is where we take into account the latency constraints, the engineering constraints, the advertiser constraints such as frequency cap, budgets, and so on. In the fourth layer is where the reward lies. So all of this, basically from impression to click to the final reward that you get in terms of purchase and so on, gets fed back into the layer, gets fed back into each of the layer where your models are now able to learn from new data. Now, for all of this to happen, your engineering systems needs to be elephant strong. They need to evolve. They need to accommodate for newer use cases from data scientists. They also need to innovate to keep pace with the ever-evolving ad tech systems. Now, how does that happen is what Raj will cover in the next 10 minutes. Thanks, everyone.
Okay, so I think Vishwa did talk about all the science problems and how to go about solving it, right? But when you are operating at like millions of requests per second scale, all of this needs to get tied together properly, orchestrated also properly, and you have to respond back, right? So how do you go about doing this at scale, and also enabling and giving enough flexibility to scientists to experiment different hypotheses, different journeys and so on and so forth, right? So before going into like the crux of it, let me also explain what we are dealing with, right? So we get a bid request, and there are n number of products that we call demands can be matched to that request, right? And how do we make sure that we respond back with one or few demands, right? A lot of filtering that goes behind the scenes, and there are different ways to do the filterings, right? And every demand comes with an objective. For example, a particular website may want to do new user acquisitions, versus a particular website or a app may want just remarketing, or they want to re-engage the users, right? So in that sense, if you see a particular request comes in, right, and based on the different objectives of the demand or the products, it goes through different journey, right? And this is what we call as funnel slash journeys, right? They look more or less same, but there are key differences here, right? Like for a new user acquisition, if I zoom in a little bit, yeah, for a new user acquisition, there is a lookalike scoring that happens because this is a cold start problem, right? So I have another way to say that, okay, some other advertisers look like this. So how do I make sure that new users are acquired in this way, right? But when we go to remarketing, there's like past purchases filters we need to do, and we need to do retargeting scores and so on, right? And this funnels and the sequencing of these steps keep changing, and we keep experimenting, saying, okay, for a particular objective, what if I do creative selection before and then I calculate the price of the bid, right? Because that also influences. So let me play around with it, and let me do a experiment with that, right? But over time, we kept getting such requests, we kept entertaining scientists, but eventually what we landed up with was this. We had a big if else jungle. For every objective you do this, then you have this thing set of rules, and then you do this. Of course, this is a recipe for a disaster in production. And of course, Vishwat was not happy, right? Because he was not able to see what exactly is configured in the system, because then he has to go through code and so on and so forth. Each iteration takes a lot more time, because now we have to test all other flows. We make sure that we don't break anything which is already existing and so on. And on top of this, when you add experimentation layer, saying, okay, I have a hypothesis that I want to do budget checks at certain point in my funnel, but let's try this on 5% of traffic, right? So this becomes even more complicated. So how do we go about solving it, right? So what we did was, first of all, we broke this monolith jungle into individual services with very well defined roles and responsibilities. And we now can think of each of this service and each of the objectives being fulfilled by this service as a composable piece in the whole journey, right? So now it's like a step-by-step process, and you can move around steps however you want. But to do all that, you need this part, which is the big beautiful orchestrator, right? So now, how do you do this orchestration? Essentially, it's a orchestration problem, right? Like I want this, after this, after this, and in any order for based on different dynamic dimensions, right? So what we did was, we took a step back and said that, okay, what are we trying to solve here? What we are trying to solve is, first you have a demand with an objective, and we know for a particular demand where do we go, how do we want to experiment with this demand, and then we say what services or steps are going to run, right? So we defined a very simple DSL, nothing fancy here. It's like plain YAML with common expression language, so that any scientist, anybody in the team can come and configure this very confidently, right? So it says basically there are different rules which says, for a particular demand with of advertiser ID or a line of business and particular country or geo, there are multiple dimensions, goes to a particular layer, right? And layer decides what is the journey it's ultimately going to take based on the split. And this is where we have the experimentation baked in, right? Once you know the journey, now we just need to look at the journey, right? How does the journey look like? Again, journey is also a simple YAML where you say what are the steps. So first step here is zero budget check, and then you do targeting, then you do quality aware pacing, and so on and so forth, right? So these becomes the step. Now all these steps give back a particular score, And the scores are used to do the filtering, saying that, okay, this demand doesn't need to move any forward because it doesn't meet the gating criteria, right? So every service can have n number of gates, and ultimately you reach a particular demand which needs to be now advertised, right? Okay, this is good. Vishwat or any scientist can come in, express this, they can read what is happening, what is not happening in the system, and all of this is compile time safe, right? So any wrong configuration gets caught at the compile time itself, right? Wow, hunky dory, we are back to making Vishwat happy, right? But the problem is when we broke it down into microservices, we are paying a price. Now every network call is adding latency to the overall processing time, right? And we have a very tight budget of 100 millisecond overall. So what we saw was eventually with the load balancers and all what that we were using, let me go back. It was taking about 1.3 millisecond at P99 to do one network call to one service, right? And when you have 10 steps, which means there are 10 10 network calls, that brings up to like 13-15 milliseconds just for the network cost, right? That's too much to pay for, uh, given that that becomes like a 15% of our total latency budget, right? So how do we go about solving this? So let's first understand why this 13 to 15 millisecond latency is added, right? So when we use normal load balancers with gRPC, of course, there are a few problems, right? One problem is the stickiness. gRPC operates on a long-lived multiplexing requests, right? So when the pod gets attached, okay, when you scale up also, it gets time to get reflected and so on and so forth, right? And the bigger problem is the hop, right? You can still solve the stickiness problem via few other solutions, but the hop still remains. Every time you still need to go to load balancer and then to the actual service, right? So your service discovery has one more hop now. So this is the main problem, right? So so now the requirement for us is how do you do service discoverability at a much lower latency cost while not adding more complexity to the system, right? So the solution that we have come up or that we implemented is Proxyless gRPC with XDS. For Proxyless gRPC with XDS, we leverage Google's traffic director, so it doesn't add any new infrastructure component for us to maintain. That is one part of it. By the virtue of Proxyless, it means that now there is no hop, right? The load balancing logic sits in my client library. What this means is now my application itself is load balancing and it has all the information needed for all the other services it needs to connect. And how does this happen is XDS is a protocol and it's you can like break it down into four main components, which is LDS, RDS, CDS and EDS, right? If I give an analogy how it works, basically let's say you want to board a flight, right? So what LDS helps you is which airport you should go to, right? Then what RDS helps you is which gate slash terminal you need to go to. Then CDS are bunch of rules saying that it has priority boarding, it has XYZ rules and so on and so forth, like what's the zone and all of that. And EDS will give you what exact agent you should contact who will help you board, right? So in this way, this makes our service discoverability much more simpler. We didn't add any more component other than traffic director, which is again managed by Google GCP, right? And with this, we were able to reduce our P99 latency from 1.3 milliseconds to 560 microseconds. What this means is overall for our request processing, we save about 10 milliseconds of latency, right? 10 milliseconds is the actual 10% budget of my total latency, right? So now this 10 milliseconds can be actually used to make further business decisions rather than just giving it to the plain and simple network hops, right? So I would say Proxyless gRPC should be explored. I think it's a great piece of technology. If anybody is looking for low latency, high throughput service discoverability solution, it's definitely one way to go. Of course, there are others. I think I saw a talk already about eBPFs at kernel level. That's also one another solution. But yeah, that's it for now. I'll now hand it over to my colleague who will talk about how the requests response path, the ML path, and uh, these two come together via the data layer. Over to you, Pankaj.
Thank you, Raj and Vishwat, for setting up the stage. Uh, we have seen the whole picture now, right? Vishwat showed us the models that data science want to serve. And Raj showed us the user journey, how each request is becoming response within 100 milliseconds. But neither of them showed us the layer in between. What each of one of those model wants, features, right? So we need to serve those features at scale, at our scale. And this is what the statement I want to make is feature store is a ML substrate, not a cache. When you stop considering it as a cache, most of our problems stop existing. So what does a feature store should promise, right? There are three things. First is one definition. A feature which is defined well at one place can be used across the place, which doesn't happen in most of our ML system. We want our training pipeline to follow the same definition as the serving pipeline. If you have different definition, your model will go haywire. You'll have different predictions. Hence, we want one definition. This is the first promise it should make. Second is every model. We have like hundreds of models running in DSP. All the models should be powered by one store. If it is not happening, it means you have hundreds of ETL pipelines generating the same data in different format, having different metrics, different outcomes. Model 1 will not be able to communicate its learning to the model 2. Third thing is zero train and serve skew. So at the time of serving, if you are calculating a feature value as 2, and whereas while doing the training, you are calculating the same value as 200, it means your model prediction is 10x or 20x. To avoid it, we need to make this promise that whatever data we are calculating at the serve time, it should be same at the training time. There are a lot of models, a lot of data sets, and different look back windows for all these features. So how are we solving it? First is you need to define your DSL, your features via DSL at one place. This is our YAML file. This is how it looks like, where you define the source of the data, which pipeline is going to calculate that feature. In this example, you can see we are calculating number of clicks a user has done in last 7 hours. So that is being generated. This data is incoming, being calculated by Paco pipeline, stored in Aerospike. Once data is stored at Aerospike, you can use it at online manner as well as offline store, and the different windows, right? 7 hours, 1 day, 30 days, 90 days, anything. Once you define this feature, it will go to a CI pipeline that will check the schema of the whatever YAML you have defined. It will check the semantics whether the data set exists or not. If this data set is existing, it will do the dry compute. It will check whether data is being calculated properly or not, whether data value seems correct or not. There shouldn't be any negative values. If it is allowed, then it should check like some other values, infinity and all. It should be backward compatible as well. So if a model which is taking different values at different time will give different results. So every model which is trained on some different value earlier, we need to check if we are changing the DSL that okay, this new model we are publishing, it should have this new value now and model is generated for it. Once this all checks are done, finally a manifest is generated. This manifest is a single source of truth now. It is powering all our offline plus online jobs, which is calculating this feature via this DSL. So where does this fit? Like we are delivering for the first promise that will follow the first one definition promise, but this is the whole architecture where it is sitting, right? So you have defined the DSL. You are getting a lot of data. All the different data points Vishwat and Raj has talked about: wins, clicks, impression, purchase, install. All these events are coming in real time. There are like hundreds of microservices getting this data, different standard they are following. We wanted to fix the data path, which is our data plane here. We are getting the data, we are standardizing it in a format that our feature stores should understand. This is where we convert the data, we generate standardized data, put it into Flink and Paco pipeline. Paco pipeline is like stateless. It doesn't know about history of that feature. It will do simple counter rollups and all. For example, click in last 7 hours is being generated by Paco pipeline in this case. Once it is generated, it will go to Aerospike as our store, which is providing us a millisecond latency for our model serving. Same another approach, another type of feature is your aggregators, which is like give me P99 value of a bid price, give me distribution of bid price within last 1 hour or last 30 days, which is being done by Flink, which is stateful pipeline for us. And once it is generated, same pipeline, it goes to Aerospike. In Aerospike, we store all these features, serving all our models. This is one part of the feature generation, right, which is online. Second part is our all the offline jobs, which are taking a lot of data, 60 days, 90 days, 1 year worth of data. Using this data, they are generating their own offline features, such as embedding, lot of LLM agent worth data. All this data is going to StarRocks, which is our second promise that we want to make, right? One store for all our data set. This is where all the data set is sitting, the online data as well as the offline data. Via this offline data, which we are generating in StarRocks, all our hourly batch jobs, daily jobs are running to generate these offline features. Once these features are generated, again it goes to Aerospike, which is our OLTP engine for all the model serving. If you look at the third promise, right, node, train, and serves queue, how are we delivering it? Here we had to make a call that, okay, Aerospike, we have all the data. Now it should be our point in time consistency metric. So any feature which is generated online is being XDR, which is like copy from Aerospike to StarRocks, so that for a given request, you have an ID. Using that ID, you know that this all features were generated in online, and those features were available in online as well as train now, because while training the model, you are querying StarRocks. To do all these things at our scale, it is very difficult and it took some time. There are a lot of setbacks, but finally when we delivered, it was like we are serving thousands of features, 500,000 worth QPS we are writing, all these bids, wins, clicks, and the model serving is at 3 million QPS. You have sub-second latency for getting the training data that we need for StarRocks, from StarRocks. And the code retention part, which I forgot to cover, but there we are having like petabytes of data because it is too much. Like, we need to put it in some other place, which is Iceberg, our secondary data, it goes there, right? Iceberg plus Polaris. So all these things doesn't come for free. It costed us, it bit us. So XDR call, as I talked about, it took us time to figure out how to make it work. All the data from XDR to StarRocks, a lot of POCs have been done to make it work. DSL is as good as your like how you are defining the features, right? If you are following that tool, you are following the CI pipeline correctly, you are not putting any logic of any business logic, feature creation logic in Flink, it will work fine. But it doesn't happen. People write their own logic in Flink and Paco code. So that we avoided slowly. Schema drift, right? Lot of all these tables which we talked about, win, click, bid, all this data have different schema. At a point where a feature is calculated, but schema is like the definition of the feature, that value, column value itself is changing, you can't avoid. So it took us some time like to generate this. Finally, coming to the conclusion, which we all three talked about, Vishwat, me, and Raj. So first takeaway is that your model, whatever you are trying to train, shouldn't get plateaued, right, over the time. There should be constant feedback loop, which will give your model a better way to take the decision at the ad serving time. Second takeaway is that your flexibility and performance shouldn't be at odds. So you design a system such that you can give flexibility to data scientists to do a number of experiments, and you via engineering you solve for performance, where you can serve those 3 million worth QPS data. Third takeaway is that whenever you design a feature store, you need to take care of multiple substrate. In our case, it is online as well as offline. So it took us some time. It dictates how you are defining the latency and all, but it should provide the one contract point in time consistency, and it should be manifest driven. That's all from us, guys. Open for questions.